It's a distinct pleasure to welcome as our Waterloo Institute for Nanotechnology distinguished lecturer, Dr. Yuan T. Lee. Dr. Yuan T. Lee is also in Canada as the National Research Council, National Science Council of Taiwan, eminent researcher. Yuan T. Lee was born on the island of Taiwan and received his BSc degree from National Taiwan University and his MSc degree at National Tsinghua University. He did his PhD at the University of California, Berkeley, under the late Professor Bruce H. Mahan, and he then stayed on as a postdoc to carry out reactive scattering experiments in ion molecule reactions. In 1967, Dr. Lee joined Dudley Hirschbach's group at Harvard as a research fellow, where they took molecular beam experimentation beyond the reactions of hydrogen atoms and diatomic alkali metal molecules into crossed molecular beam experiments. Now, I think Dr. Lee will explain what that means. As an assistant professor at the University of Chicago in 1968, he rapidly made his laboratory the North American capital for studies of fundamental chemical processes in reactions in molecular beams. Dr. Lee returned to Berkeley as a full professor in 1974 and significantly expanded his research to include, in addition to crossed molecular beams, studies of reaction dynamics, primary photochemical processes, and the spectroscopy of ionic and molecular clusters. In 1994, he retired from his position of university professor and principal investigator at the Lawrence Berkeley Laboratory and took on the post of president of Academia Sinica, the highest-ranking academic institution in Taiwan. Academia Sinica consists of 30 independent institutes and more than 250 academicians. And during his presidency there, I think it's fair to say that he transformed Academia Sinica into a truly world-class research organization. In 2006, he became professor emeritus and distinguished fellow at the research fellow at the same institution, and he will continue his research at the Institute of Atomic and Molecular Sciences and the Genomics Research Center in Academia Sinica. In 2008, he was elected president of the International Council for Science, often known as ICSU, which will begin in 2010. Now, Dr. Lee has received many awards and honors, including the 1986 Nobel Prize in Chemistry, jointly with Dudley Hirschbach of Harvard and John Polanyi of Toronto. And it's an interesting fact that the University of Waterloo beat the Nobel Committee to the punch by awarding Dr. Lee a U of W Honorary Doctorate of Science before his Nobel Prize was announced. Among many other awards, there are many I can tell you. He has won the U.S. National Medal of Science, the Faraday Medal and Prize of the Royal Society of Chemistry, London, and the Jawaharlal Nehru Birth Centennial Medal from the Indian National Science Academy. He's also been awarded the Ernest O. Lawrence Award of the U.S. Department of Energy, the Harrison Howe Award, the Peter Debye Award of Physical Chemistry from the American Chemical Society, and the Othmer Gold Medal from the Chemical Heritage Foundation. He's also a fellow of many academies, including the American Academy of Arts and Sciences. He's a foreign member of the U.S. National Academy of Sciences, the Göttingen Academy of Sciences, the Indian Academy of Sciences, the Korea Academy of Science and Technology, and the Royal Swedish Academy of Engineering Sciences. That's only a few of the things. He has received honorary doctorate degrees from no less than 35 universities around the world, including, of course, his Doctor of Science from Waterloo in 1986. Now, I've known Dr. Lee for many years, and we meet at least 2 to 3 times a year as council members of the Science and Technology in Society Forum, STS in Japan as it's called, and also through the Science and Technology Advisory Group, STAG, of the Government of Taiwan. Dr. Lee is a personal friend. I value that, and he's also a friend of Canada, and it's a real pleasure to have him back to visit us once more in Waterloo. So please welcome Dr. Lee for his Wynne Distinguished Lecture entitled ionization processes of molecular clusters.
Well, Professor Carty, thank you very much for a very kind introduction. It is a great pleasure to come back to the University of Waterloo. It was almost 23 years ago when I first visited University of Waterloo. And as Professor Carty mentioned, I received the first honorary Doctor of Science degree from this university. And I really appreciate it. And that was, as he mentioned before, the Nobel Foundation announced that they will give me the Nobel Prize, and Waterloo is the only institute I visited in between the announcement and awarding the Nobel Prize. Professor Carty, as he mentioned, was a good friend of mine, and the reason I'm here is really due to his effort of establishing National Research Council and National Science Council of Taiwan, and established very strong collaboration in promoting scientific change. Today I feel very honored to present a lecture. The topic is called Ionization of Molecular Clusters. The cluster I've been talking about, I start with a very small cluster of the atomic molecule, and then go to a big cluster, millions of molecules together in the stellar condensed phase. Actually, I started to work on the process so-called MALDI after I retired from my presidency in Academia Sinica 2.5 years ago. At the time, the new president asked me, where are you going to move into? It's a very nice office in the Center for Genomics. There's a building, a new building. The 7th floor is a wonderful office. So I decided to move into that office. Then he asked me, but you have to help us on the mass spectrometry of biological molecule. There are lots of questions. It has not been answered yet. So I said, okay. So during the last 2 years, I've been working on the process of MALDI, and I'll try to tell you what's going on in MALDI. It has not been very well understood in the past. I'm a very old-fashioned person. I don't have a very colorful slide to dazzle you, but very old-fashioned transparencies and very simple pictures. Actually, it was interesting. About 30 years ago, when we are looking at the van der Waals molecule, there's a question of how strongly van der Waals molecules bond. We can do scattering and measure angular distribution and obtain the potential almost exactly. At the time, at the University of Waterloo, there's a professor called Jacinto Scoles. He was using bolometer to measure the angular distribution the similar way as I was doing in the universal cross molecular beam apparatus. So we became a very good friend with a lot of interactions. At the time, there was one question. If you look at the argon molecule ion 2 plus, how strongly will those bond? So I said, well, I'll find it by photonization, argon 2. Lots of people said, oh, you could not find it because argon 2 is a very loosely bound molecule, van der Waals molecule. The bond distance is about 3.76 angstrom. Argon 2 plus is very tightly bound, chemically bound species. So because Frank-Condon factor, you will never reach that bottom of the argon 2 plus. But I said, well, that's not quite true. Because there are lots of transitions in the atomic transition. So if you look at the atomic transition, there are many transitions. So when you have argon 2 bound together, it is possible to excite those bond state in the atomic species. Those are also start to interfere when atom brought close together. So in a sense, even the atom is far apart. When you excite the electronic excited state, the interaction will bring them together, and you can call it the vibrational pre-ionization or associative ionization, you can produce ion and you can search for the bottom of the well. And so you can see in the experiment, you do see lots of bond-to-bond transition that correspond to atomic transition in the argons. And we found in this ratio is around 117275 wave number. That shows that the argon 2 plus is bound by 1 eV. Later, it turned out to be very accurate number. But the interesting thing is that just show that the photon excite the molecule to search the way through. But when you have water molecule, it's more complicated. When you excite, it's not just moving close together. You have to rotate and many coordinates has to move. So I do not think I will be able to find the bottom of the well of two water molecules. But on the other hand, when you increase the photon energy, gradually increase the photon energy, then the maximum excitation of ionic species will be equivalent to when photon leave the molecule with zero kinetic energy. So in a sense, ionization can control the maximum internal energy of the molecule by tuning the wavelength. So when you change the wavelength and going up until a certain point, the internal energy of the water molecule diamond ion will be enough to induce the chemical decay and form protonated water molecule. And here you will find this ratio. It means this ratio is really controlled by controlling by maximum vibration energy of the molecular ions and induce the decay. So that will give you the proton affinity of water molecule, because ionization potential is known, dissociation energy is also known. And that proton affinity determined by this method is a 167 kilocalorie. And that turned out to be a very accurate number up to present time. Well, when we are working on this hydrogen water molecule dimer, one day, Professor Schaefer came one day and said, Yuan, we have been calculating the cluster of hydronium ion. And he said, the best way to understand the solvation process is to take the hydronium ion and put water one by one. And he did the calculation, shows that at that time he thought the hydronium ion with one water attached to it is more stable than proton shared by two water molecules. And he went on to do calculation of many species. But the interesting thing is he said, I can calculate those molecules, but we will never be able to do experiment to determine the structure and tell me whether I'm right or wrong. And that was a big challenge for the experimental scientists. The reason is, when you make the ionic species like this, and you send through the mass spectrometer, density of ion will be so low. You shine the light and try to measure the absorption, you cannot measure the absorption. So in order to do the experiment, you do have to find a way to distinguish the molecule in the ground state and those molecules which absorb 1 photons, vibration excited molecule. That was in the middle of the 1970s. We have been working on the process called infrared multiphoton excitation and dissociation of a molecule. And that is really quite excitation laser chemical processes. If you have a molecule, you look at the transition from ground state to the vibration excited state. Because of the anharmonicity, if you pick the infrared photon frequency, energy, you will not be able to put more than 1 photon into the molecule. But if you have high power laser, excitation and stimulated emission will be taking place in such a short time. It's a phenomenon called pop broadening. That will broaden up. But if you have a polyatomic molecule, how can the polyatomic molecule keep on absorbing infrared laser, infrared photon, and induce the dissociation. At that time, a lot of physicists working on this didn't understand what's going on because power broadening is not enough to overcome the antiharmonicity, and until later on, understood that rotational compensation is important. If you have the polyatomic molecule, when you pump from V equals 0 to V equals 1, induce the rotational transition, and rotational quantum number go down by 1, P transition, Q transition, R transition, then rotational gap will compensate for the anharmonicity. Then you can put the photon into the molecule one by one. So, realizing that, we thought there's a way to distinguish the cold molecule and hot molecule by using second laser to tear apart the hot molecule and induce the fragmentation. If the cold molecule will not fragment and hot molecule fragment, then like doing double resonance, it is possible to measure the absorption of the molecular ion. Even the density is very low. So we produce the coronal discharge ion source through the expansion, produce clusters, and go through magnetic mass spectrometer. Here we have a quadruple lens pair to squeeze the beam and make the beam parallel in one direction, use the electron focusing or magnetic mass spectrometer to focus the ion. And then we use the quadruple lens pair to bend the ions. So this axis will be the experimental axis, laser will be shined in and out. We did send the ion into the octuple ion trap. At first exit state is high voltage, so ions will be trapped in there and running back and forth. Idea is very simple. If I have a tunable laser going in, and I don't know whether the molecule is excited or not, then use a high power CO2 laser, send it in afterward. If the molecule is excited, then the CO2 laser will tear it apart. So after a lower the potential, push all the ions out and using quadruple mass spectrometer to measure ion one by one, and then you will get the spectra look like this. Like you take the 5, 6, 7, 8, 9, and you can do really look better spectra like this. The interesting thing is this. If you look at the proton with 5 water molecules and look at the spectra, they are, because OH stretching is well isolated. So you can see those water molecules on the outside, the symmetric and the anti-symmetric stretching showing up here. And the new feature showing up is really due to the fact there's another one, another free OH sitting here. And this yellow color one is showing the structure here, and this hydrogen bonding will be here. So these are shown by these arrows and showing different regions, showing different vibration. And the very interesting thing is when Professor Shaver did the calculation, he posed a very interesting question. If I have an even number of water molecule, would proton sit in the middle? And this experiment shows that the spectra show two structures, both structures are stable and does coexist. For example, if you look at this structure, hydronium ion with 3 water molecule in the first sorption shell, and then second layer water molecule go in the second sorption shell. There you do see spectra, symmetric, antisymmetric, and these two structures. If the structure is a proton in the middle, then you will only see these two, will not see this free OH showing here. And the hydrogen bonding in this part will show a feature shown here. So this spectra shows both features are in the spectra and shows this and this are both stable. It's not, one is not the transition state for the others. It's both are stable species. Of course, once you break the symmetry, proton will move from the middle to one side. And that was really quite interesting. But today, as I said, I want to go into a large molecular cluster. Cluster shown here with the millions of molecules. And what I want to talk about is really the process called matrix-assisted laser desorption ionization. It's called MALDI, desorption ionization, ionization desorption. It's called MALDI. What's happening here is you have a biological molecule called ionite put in the matrix. And then you shine the laser. Laser will evaporate the matrix and ionite together. And after the evaporation, some of the ionite will be ionized. So put into the gas phase. Biological molecule is not volatile. In the past, people have not been able to do mass spectrometry. But if you can put the molecule in the gas phase, like those people have done, this there shows the history of mass spectrometry. You go through the development of various mass spectrometry. It's interesting. The year 1983, about 26 years ago, they can make a tremendous difference of mass spectrometry application, because that's the time Tanaka and Hillenkamp and Karas developed the method called matrix-assisted laser desorption ionization that allowed them to put the biological molecule into the gas phase, and you can do sequencing, proteomics, and tremendous development happened afterward. Before then, mass spectrometry in biological molecule wasn't that important. So the year, I think 2002 or 2003, Nobel Foundation gave Tanaka a Nobel Prize. The same year, John Fane, who developed the electrospray, also received the Nobel Prize together with Tanaka. But the interesting thing is this method has been developed for more than 25 years, but people still do not understand what's going on. And many of the experiment, they will use the matrix for different purposes. For example, here show the structures. For glycoproteins, glycolipid, carbohydrate, using 2,5-dihydroxybenzoic acid. So these different matrices are used for different compounds, oligonucleotides, and use nicotinic acid, and so on and so forth. And very often used one is 2,5-dihydroxybenzoic acid. If you look at those compounds, there's one common feature. There's aromatic ring there. The reason there's aromatic ring is because if you have an aromatic ring and attach some derivative, that ring will absorb the photon in the 30 nitrogen laser, 3200, or YAG laser, 3500 region. So aromatic ring is really there to absorb the photons, to energize the matrix, to evaporate or decomposes. And there are hydroxy functional group or carboxy group, those tie them together, so there will be hydrogen bonding. So when you use the matrix, put the analyte into the matrix and put in the vacuum chamber, you pump it. It will not evaporate. It still remains there. So when laser comes in, then induce the decomposition or ionization. Of course, sometimes you might think that the carboxylic acid or hydroxy acid must be responsible for the ionization process, for example, like proton transfer. Before I go into the detail of what's going on, I want to give you some phenomenological feeling of what's going on MALDI. That was the experiment done by Purisky and co-workers done in 1999. Laser will hit the surface and sample start to evaporate. And as a functional time, they use a seesaw laser to do laser-induced fluorescence. So they tune the two frequencies. One is matrix frequency. So look at the 5 microsecond, 10 microsecond, 16, and 20 microsecond. You do see the plume develop. And the color doesn't really show that this is red hot. It's just laser-induced fluorescence. If you put the protein dye and using laser-induced fluorescence, 5 microseconds is similar, but gradually you see it's thinning out and lag behind. Like if you compare 20 microseconds, it's moved out to 2 centimeters, and 2 centimeters here is way behind, and velocity angular distribution also narrowing. So matrix and analyte, when expand, seem to expand similarly, but immediately there's a phase lag lagging behind. And if you look at this time scale, those plumes are in the microsecond region. But when Kubernetes and the coworkers look at the temperature after laser irradiation, it's a YAG laser, 5 nanoseconds, for which have maximum irradiated on the surface, and look at the infrared emission by using indium gallium arsenide photodetector to monitor the fluorescence coming from the surface and try to understand temperature. They did find actually temperature trace the laser profile very closely with a time delay of only 5 nanoseconds. Going up and down, so after 10, 20 nanosecond laser, it's very cold, very cold. So plume showing microsecond, that probably has nothing to do with the initial ionization. There are lots of mixing going on, especially proton exchange going on in the plume. But ionization process does not have anything to do with the plume. Well, let us understand what's going on there from the phenomenological point of view. If I have a molecular beam source, the molecule contain, here I show 2 different gases, red gas and red molecule and blue molecule. If you look at the motion of molecule inside the tube, if the red molecule is heavier one, you have a maximum Boltzmann distribution with the peak velocity loss smaller than the blue molecule if the molecular weight is lost smaller. So you do have 2 molecules with different velocity distributions. If I were to allow them to expand into the vacuum chamber, it will be isentropic expansion. Enthalpy should conserve. So behind the nozzle, mass velocity of the molecule will be moving about 1 or 2 centimeters per second. On the other hand, molecule inside, if there's a nitrogen molecule there, it will be moving around 3 times 10 to the 4 centimeters per second, about the speed of 747 flying. So that mass velocity, mass kinetic energy compared to thermal energy is almost 0. So the enthalpy of the gas, if this is the gas system, should be 3/2 kT plus PV equals kT. Another. So enthalpy should be 5/2 kT. After the isentropic expansion, if you expand from one atmosphere down to 10 to minus 4 expansion is so high, where temperature go down to almost 0. So here, after the expansion, thermal energy will go down to 0. Every atom will be moving at the same speed. So you will see after isentropic expansion, velocity will become very, very narrow because temperature is very low, and average kinetic energy will be 5/2 kT. So here, I show the equation. 1/2 mv, this is average mass number. That's the kinetic energy of the moving molecule. That should be 5/2 kT. Of course, if there's a heavy particle and light particle, heavy particle kinetic energy will be 1/2 big mv prime square. That I can rewrite in such a way that would be the same as average kinetic energy times the mass ratio. Mass of the heavy particle over average mass number. So you can imagine if I put the xenon in the hydrogen molecule and expand it at 3000 degree K, xenon we have 132, and average mass number, if you put 1% in the 99% of the hydrogen, this will be something like 3.33, right? 1% of 133 times 99% of 2. Obviously, the mass number will be 3.3. So this will have a factor of 40. So if I heat up to 3,000 degrees, xenon will be moving with the same speed as a hydrogen, except xenon will have about 20 eV, enough to break up many chemical bonds. And this is interesting. But the interesting thing, what I'm trying to tell you is, if this is not a molecular beam expansion, if I have a laser shine on the surface, when it started, pressure is high. So everything will be expanded like isentropic expansion with the same speed. Then as soon as the expansion takes place, pressure becomes lower and gradually move into the molecular flow. So when you shine the laser in the MALDI process, initially all the molecules will move at the same speed. And then gradually light molecule move faster, heavy molecule be lag behind. That's why we are seeing that kind of phenomenological things, that the fast particle and slow particle is lagging behind. Let me ask the question, or the key question. Over the past 20 years, more than many thousand papers published on this issue, and then Kukamo's mechanism seems to be the one which is accepted. The question is, why the matrix molecule after excitation is ionized? How is ionized? Kukamas, when he studied laser intensity dependence, he came to the conclusion that it takes 2 photons to produce ions. But 2 photons is not enough energy to ionize the matrix. So he suggested what's happening is if you have S0 excite S1, another photon will excite another molecule. Then, because of the energy pooling, one of the molecules go up to the Sn state, accumulate 2 photon energies up there, one will go down. Then another molecule, which is excited state, will collide with highly excited molecule. Then will produce ion, and one go down to the ground state. This is called energy pooling mechanism. Well, that concept is certainly quite reasonable if you have an isolated molecule. If you have an isolated molecule, and you said how the molecule ionizes, you have to have enough energy beyond the ionization potential, then you remove the electron, produce ion. But this is not the case. It's not in the isolated molecule. He was talking about energy pooling, energy flow from one molecule to the others. So first, the first question I will ask immediately is, how come the electron transfer or proton transfer is not important? Because if you look at this, you have 2 molecules sitting side by side, and you ask, how much energy does it take to move proton from one molecule to the others for MH plus M minus H minus? The hydroxybenzoic acid, it will require 5.24 eV. 3-hydroxyacetophenone, is known as PAIP, will be 5.18. Even if you transfer electron like the hydroxybenzoic acid, only requires 7.5 eV. So if you have 2 molecules, there are no energy channel, then the channel which require molecule to remove the electron. So my question is, why proton transfer, low energy channel, is not important in that process? People seem to neglect this. Of course, after the ionization, during the expansion process in the plume, there will be lots of proton transfer reaction taking place. So it's not surprising if you take glycine, proton affinity is 852 kilojoule per mole, and you use the matrix THAP, proton affinity is 882 kilojoule per mole, then the higher proton affinity will grab the proton. So after the look at the MALDI, the ion will be THAP plus H 169.1, and look at the signal of the glycine, no signal. And now you can change the matrix by using CCA, proton affinity now become lower, 764 kilojoule per mole. Glycine will be higher, so glycine will grab the ion. So proton transfer is taking place. There's no question on that point. But again, I want to come back to how the ions are produced. If you look at the isolated molecule, THAP, if you take the laser, excite the molecule after the electronically excited state, first electronically excited state, in isolated molecule, nothing much will happen. Maybe you see fluorescence. But once you put another photon into the molecule, then internal conversion is going to be very fast. After internal conversion, you have a hot molecule. Hot molecule will speed up the hydrogen molecule, will start to dissociate. So after absorbing 2 photons in isolated molecule, the most faster channel will be eliminating 1 hydrogen atom. And we've done in the beam. So the beam molecule, 2 photons in, sure enough, the faster reaction will be eliminating 2 photons. After you put 1 more photon in there, then you will be able to ionize the molecule. Now enough energy to produce THAP ions. So in the molecule, you tune the intensity. You have to have a very high intensity to go through 3 photon process to remove the electron. Most of the cases, after absorbing 2 photons, eject the hydrogen. Now, I'll take 2 molecules together and then ask the question, what will be the difference? If I take 2 THAP together and form the THAP dimer, let's line up the zero energy with the isolated molecule, and this binding energy might be only 4 kilocalorie, 4.9 kilocalorie per mole. Now the interesting thing is, if I were to put 2 photons in, the internal conversion will be fast. But when you put 2 molecules together by hydrogen bonding, weakest bond in the dimer will be the hydrogen bonding, not the CH bond anymore. So after internal conversion, all molecules dissociate by breaking hydrogen bonding. So that will be what you see. The molecule will be highly vibrationally excited. So 2 photons will go through internal conversion, will not speed up hydrogen atom anymore. It break the hydrogen bonding. But amazing thing is, if you have 2 molecules together, you put 2 photons in there, there's 1 channel which will become open. That will be proton transfer channel. It will only require 5.15 eV. And that should be much lower energy than ionization potential. So at first I said, well, I can easily show if I take 2 THAP together, produce THAP dimer in the beam, and adjust the laser intensity 2 photons in there, I can show proton transfer. But I didn't see that. I didn't see that. If I tune the laser intensity higher, then you will see ion produce, dimer ions, you can see those. But those are not efficient process. Well, then you ask questions. If I have a water molecule and ask, what is the proton affinity? As I said, we've done the experiment, 167 kilocalorie. If you take that hydronium ion, bring another water molecule, will release 25 kilocalorie. So bound by another 25 kilocalorie. So if I have 2 water molecules and bound together and ask, what is the proton affinity? That should be 25 kilocalorie more than 1 water molecule. If I put 3 water molecules, then if you have hydronium ion with 1 water, release 25 kilocalorie, another water molecule will release another 15 kilocalorie. So if you have a water molecule trimer, proton affinity will be increased by more than 40 kilocalorie. So the question here is, if I have THAP all bonded together, there are many hydrogen bonding, then energy released by proton affinity should be a lot higher. So even if you have one isolated molecule, transfer proton to the THAP trimer, that 5.2, 5.15 should be lower, even more. Negative ion produced by hydrogen bonded species also should lower the energy. So the question is, how low would that energy go? And that is not really well understood, especially the negative ion side is not very well understood. But anyway, in the laboratory, we thought, okay, if we believe proton transfer is important, we should be able to show in the carrying out the experiment and measure positive and negative ion and show positive ion is always plus 1, negative ion is always minus 1. So we constructed the machine something like this. With laser will shine on the sample, produce the ion. So one side will be looking at the positive ion, other side will be looking at the negative ion. And if you look at the insulin B and myoglobin, roughly saying that what we are saying is right. They measure same time, you positive ion and negative ion, and one side is plus 1, one is minus 1. So proton transfer mechanism seems to be taking place. Of course, there are some complicated mechanism. Here, insulin B will have 2 protons attached to it, so doubly charged. And let's see, when you look at the positive and negative ion, you want to make sure correction efficiency is the same. When we designed our machine, so when you move the laser, efficiency of measuring positive and negative ion will change, and our measurement seems to show that that is correct. Other interesting thing is when we mix many analytes together and try to analyze it, in the gas phase, proton transfer is so facile, then the day should be winner take all. The one with the high proton affinity will be the only one exist, but that's not what's happening. Local equilibrium is established. There are a lot of proton transfer between analyte and the matrix, but between analyte so far apart, its exchange is not taking place. Then you ask the question, why there's so much complication in MALDI, so people have not been able to understand? One of the reasons is, if you want to do some analysis here, I take example of special those things mixed with the ion intensity as a function of UV absorption, and one species we are looking at I didn't say which. We see ion intensity or insulin B. Actually, this is insulin B. Because when you use different matrix, you adjust the laser power, you see the signal. And most of the people will be happy, I see the signal. So doing analysis of what's going on. And then you tune the laser intensity a little higher, signal disappears. If you use different matrix, signal appear later. So that appearance seems to have something to do with the absorption cross-section. We have a large absorption cross-section appear earlier. But in the very narrow laser intensity range, molecule disappears, ion disappears. Shows that the dissociation must be very important. And because of the dissociation ion, makes the MALDI very, very difficult to do quantitative analysis. But once you put the ion into the gas phase, you can do something afterwards. And actually, MALDI, one thing is, when you tune the laser intensity, ion dissociate. In addition to that, you make the sample, put the analyte in the matrix. It's not a single crystal in amorphous. You saw sometimes you form the crystal on one side, there's no crystal, so people will find sweet spot. You shine the laser at a certain point, you got a lot of signal. Another point, there's no signal. So in a sense that the data is not very reproducible. So it's not reproducible, certainly. You cannot make sense out of it. So, but somehow people believe that the laser fluence is more important. It means the total number of photons going through is more important than the intensity. At the same time, people said that the 2 photons is the important, the key to get this going. So let me briefly go through the complication of laser molecule interaction. Even a molecule is isolated. Not to mention in the matrix, there are lots of hydrogen bonding, amorphous, and morphology is different. And when laser shine, reflectivity also different. And how can we understand non-reproducible condition, yet we can put ion into the mass spectrometer? How can we understand? Before we go back to the complex system, complicated molecule, I'll take nitroethane as an example. Nitroethane will absorb CO2 laser photons around 10 microns. So I use a high power laser to irradiate. I can induce multiphoton dissociate, excitation, and molecule dissociate. But if somebody asks me, what's the laser power, or what's the laser fluence you use to dissociate this molecule, first question I'll ask is, what temperature? For a given temperature, that molecule will have different rotational distribution. If I want to pump the molecule into the quasar continuum, rotational transition has to compensate for it. So if I do high temperature and low temperature, efficiency will be different. Okay, if the temperature is high enough, if the laser is high enough, I can excite all the molecules to the quasar continuum. Laser power is not high enough, I will probably only excite 10% of the molecule in the quasar continuum. So certainly intensity of the laser is important for the given temperature. What's the friction on the molecule you can pump into the quasar continuum? Your laser, like this laser, pulse laser, you can make it very intense or very weak, contains same number of photons, and this is called fluence. How many number of photons in your pulse? Integrated numbers called fluence. Now if I assume, if I excite the molecule to the quasar continuum, if I have enough photons to keep on pumping absorption, stability, emission, if the intensity is low, the process will be very, very slow, but doesn't matter. So as you have enough photon to excite the molecule, eventually you reach certain energy level, exceed the potential energy barrier for concerted decay. So this molecule will vibrate, and then sometimes molecule will stretch, sometimes will form the cyclic transition state. If you form the cyclic transition state, break 2 chemical bonds and form 2 new chemical bonds and form C2H4 or HONO. This is high energy, energy channel by vibrating the molecule and break the CN bond. So if I use the weak laser, pump slowly, pump very slowly, then eventually everything will be leaking out into C2H4 plus HONO. On the other hand, I use the same number of photons, very intense. Then this process becomes very fast. Even if the energy up to this beyond the dissociation energy limit, because intensity is so high, up pumping speed is high, so molecules start to climb up. Because density say is higher in the excited molecule. And then molecules start to dissociate from this channel and other channel. If the energy level is even higher with high intensity, because A factor, statistical factor for breaking the bond is low higher than forming concerted molecular decay. So you can use the high power laser to decompose most of the molecule with the radical channel. So it means that if you have the laser what's the intensity will determine what's the fraction of molecule. You couple into the continuum, and total number of photons will dissociate. What's the fraction of molecule will dissociate. If molecule, the laser intensity is low, then we'll be exciting with this distribution, only 20%, 30% dissociate. But if you have enough photon, all the molecules dissociate. Dissociate into molecular channel or radical channel. Again, depend on the laser intensity. So laser intensity and total number of photons and laser intensity in 3 different stages control the fate of the molecule. This is the isolated molecule. Really haven't looked at the molecular interactions. When we are looking at this, many people will say that when you shine the laser, ion produce probably less than 1 part per million. The rest is the neutral. So shine the laser, matrix absorb the laser photon, evaporating or decomposing, something come out. Only 1 part per million is the ionic species. Even the analyzed neutral is much more than ions. So when we start to investigate in this MALDI process, we did recognize it is important to look at the neutral. What's going on with the neutral species? Otherwise, you will not be able to understand the molecular decay. So I went to the warehouse and dug out the machine. This machine was built about 30 years ago at Berkeley, and it moved back to Taiwan. Except after I returned to Taiwan, we built another machine which is a lot better than this. So this is put in the warehouse, and we are using the better machine. So when we decided to look at the neutral, we dug it out from the warehouse and set it up. And instead of doing cross-beam experiment and measure angular distribution and velocity distribution, we replaced one of the beam by MALDI holder, and then we shine the laser. Here we can rotate the detector and look at the neutral and also measure the ions for the same machine. And what I really want to show you is when you look at the ion and neutral and look at the power dependence, energy dependence, and see what's going on, it is quite interesting. Next, transparency shows that the 100 joules per square meters, you do see ions, THAP. We're using metrics to understand what's going on. And then you look at the neutral. There are 43, 41, 39, 18. So we are using mass spectrometer to monitor what's going on. And you pay attention to this part. Next one, we increase the energy to a factor 2. Neutral fragmentation really increase. Ion doesn't seem to change very much. So the first impression would be when you shine the laser, matrix decomposes and lifted up the ions. Whatever ions produced will be lifted up. But that's not quite true. Now if you look at another laser intensity go up to 400 joules per square meters, then ions start to decompose. That is for sure. Ions decomposing, but the matrix molecule decompose. The best way to check it out is to measure the velocity. So because with this machine, you can measure the velocity by time of flight method. So when we look at the velocity distribution by time of flight, mass 42 acetyl group C3CO compared to THAP, the time of flight shows this almost the same. Otherwise, the light particle should move a lot faster. That's not. At the end, it's all the same. So it shows that the molecule is not dissociating. Ion will start to decompose, but at various laser intensity, the flight time is the same. Molecule is not dissociating. Look at the 69. Also, right time is the same. Although molecule is vibration excited, so electron bombardment start to fragment those into a small fragment. But molecule matrix is moving it's along and it's not decomposing. Ion is the one which is decomposing at the higher intensity. And this is the most revealing data we got. If you change the fluence, because the laser pulse is the same, so when you change the fluence, actually we are changing the intensity. The same thing. We change the intensity, change the fluence, total number of photons is increased in proportion to the intensity. If you look at the neutral species, this is about 6 orders of magnitude difference. As I say this a million times. So when you start to increase the fluence of the laser or intensity of the laser, ion species, ionic species start to decompose. So in a very narrow range, like factor 2, molecules start to decompose. So lots of people think that it's a two-photon process. Molecules start to decompose. But if you look at the neutral, it didn't decompose, keep on going up. So by the time you put lots of laser intensity in there, the difference could be 8 orders of magnitude difference. If you see that the molecule is not decomposing, then what happening must be absorbing the photon and molecule is evaporating. So look at the fluence dependence or intensity dependence and ask the question, what will be the energy of evaporation? And actually, energy of evaporation is known for those more compound. Sublimation energy is known. And that might be 100 joules per mole or something. But the interesting thing is, if you believe the molecule is evaporating, and then compare to this ratio, look at the energy fluence, and what would be the energy induced the proton transfer. The energy comes down to be very low, around 3 eV. What does it mean? It means that if this measurement is correct, it means the proton transfer has nothing to do with the electronic excited state. Matrix absorbing the photons and heating up the matrix. And heating up the matrix, temperature rises to 500, 600 to 1,000 degrees. Proton transfer takes place in the ground electronic state. Nothing to do with the energy pool in there, nothing. I was a little bit shocked. But then we did something quite interesting. Karas keep on saying that the MALDI process, if you mix them together, ion is preformed. What laser is doing is the cluster evaporation. Evaporate the entire thing, but ion is preformed. So when we put deuterium molecule in outer penthouse, carbohydrate has a high sodium affinity compared to matrix. So if you have a sodium, you can see sodiated species very easily. You can put sodium, or you can have a potassium. You can put potassium iodide, or put the old signal in the potassium attached to it. But the interesting is when you put D2O, deuterium will exchange with H2O very quickly. Water molecule in the MALDI is inert because proton affinity is low, will not compete with proton. But the amazing thing is, once you have a proton, if you have water, proton will migrate very quickly. So you can do titration of hydroxyl functional group by putting D2O, and you count the different masses. Those masses will correspond to one deuterium replace hydrogen, or 2, 3, 4, and count those numbers will be exactly the same number of hydroxyl group. When you have deuterated D2O in the molecule and you do MALDI, that's what you see. This is the sodium, and actually I should compare this with that. But after you put D2O in the sample, pump for 3 days, and then do it, then you come back to this. It means if you mix the D2O with the matrix, the deuterium exchange is not taking place. So what Karas was saying was not right. Ion is produced by laser, and after laser irradiation, ion start to exchange, and ion is really produced by laser, not by itself. But ion production is thermal. Also, next, when we get signal to noise ratio improve, then we come back to look at the so-called power dependence. Here is a commercial equipment use fluence of 0.8, fluence of 0.825, fluence of 0.85. So fluence increased by 7%. Pulse is the same. Intensity is increased by 7%. If this is really a 2-photon process, then 7%, 1.07 to the second power, only each signal should only increase a little bit. But look, from 0.8 to 0.85, signal from couple hundred go up to really 8,000, something like this. Increase tremendous amount with small change of the lasers, laser intensity. That will only occur if you are looking at chemical processes like thermal dissociation, and ion produced is only 1 part of 10 to the 10th, for example, or 1 part of 10 to the 8th. If you increase the temperature by a factor 2, exponential function kT increased by a factor 2, then you can move from 10 to the minus 10 to 10 to the minus 5 by factor 2, because those are all very small events. It's an exponential function will do that. Nth power will not do this. So this again shows that it's really a thermal process. MALDI is a thermal process. And then come back to this picture again. You use different matrix with a different absorption cross-section. And if you look at different cross-section and look at the laser power dependence, if 2-photon process or 3-photon process is important, the signal will be very, very differently. But if you look at the peak position and absorption of the matrix, almost inversely proportional to it, it means absorption cross-section really determine the temperature. And the temperature determine the MALDI process. And that was really quite an interesting discovery, working for quite a long time. And last month, we finally realized that the MALDI is a thermal process. And the key is sorbate species proton transfer to take place at very low energy, no 5.2, 3 eV, or 2 point some eV proton transfer. Well, by understanding this, the next question is, if you want to do carbohydrate, how are you going to do it? If you want to do MALDI, you want to be able to evaporate the analyte at as low a temperature as you can. Of course, if proton transfer is thermal, then if you lower the temperature, proton transfer will be slow, will not be very facile. So it's an interesting question. And can you find molecule which, after hydrogen bonded, proton transfer take place at much lower energy? Because if I can find a molecule with a small molecular weight at room temperature, which might be very volatile, but I can put in the cold button using Peltier effect, cool it down before you pump it, make it into a solid, a very reproducible ice, and radiate, the final temperature will be lower. So as you can produce ion at low energy, then it probably a better approach. But now, understanding MALDI is a thermal process will allow us, or we will be in a better position to optimize this MALDI process to improve something we have not been able to do, like carbohydrate, complicated carbohydrate. Why cannot we do MALDI? The main reason is ion has been really decomposing. It's not the neutral, it's ion decomposing. So we have to lower the temperature. If you lower the temperature, still will be evaporating. Could we transfer the proton later on? And we have been doing that by doing MALDI or carbohydrate and use proton. Actually sorbate the proton and transfer it to the neutral. And we are going to see very good signal. But we are in a position to improve the MALDI process since we now understand what's going on. Well, thank you very much. I want to show my coworkers. When I went back to, when I went back to Taiwan, I became the president of the academy. So I made it to a point, I do not want to be a principal investigator. Instead, I asked a couple young, brilliant people to come back to Taiwan, and I told them, you will be the principal investigator. I work with you as a research assistant. So I'm a president, and under me, there's a directors, and then there are lots of scientists on the principal investigator. I work under them, so-called assistant. So I told them that if machine breaks in the middle of the night, don't call me, I'm not the PI anymore. And after I retire from the presidency, when I started to work on this program, two of the scientists said, we have somebody called Dr. Tsai. He didn't seem to be motivated, and he didn't work very hard. And then he said, you just step down and you don't have anybody to work under you directly. Could you motivate him? So he joined my group. He's a very highly motivated scientist now. And all the work I shown on those are done by him. And we are collaborating with Yuan, Dr. Ni's group, Dr. Lin's group, and Chan's group. But all the experimental data was done by Dr. Tsai. So I found this really stimulating to be able to motivate so-called unmotivated scientists. And that's a really important thing. Well, thank you very much.